January 1939, Altoona Testing Plant, Pennsylvania. The engineering consensus from America's most respected locomotive designers could never have predicted what Pennsylvania Railroad officials were witnessing on the dynamometer track. A massive experimental locomotive generating thrust measurements that contradicted everything conventional steam design said was possible for sustained high-speed operation. Through the steam and coal smoke of the testing facility, the S1 prototype thundered forward at speeds approaching 90 miles per hour with stability that seemed impossible to conservative railroad engineers. No conventional wheel arrangement, no proven axle spacing, no design precedent from successful passenger locomotives. Yet it operated day after day in conditions that would have torn apart traditional rigid frame engines. Back in the boardrooms, executives were already debating the future. Diesel-electric technology promised efficiency. Streamlined designs offered modern appeal. Reduced operating costs seemed inevitable. The future of American railroading would surely require abandoning steam power entirely. The S1 was proving something completely different. Unprecedented wheel arrangement, radical streamlined casing, experimental running gear built for speeds that terrified veteran engineers. 5 years later, that same prototype locomotive would be hauling the railroad's most prestigious passenger trains while conventional designs struggled with wartime demands. The specifications had arrived at the Pennsylvania Railroad's engineering department in early 1934 with the kind of ambitious vision that made conservative designers nervous. The railroad wanted a locomotive that could haul 1,000-ton passenger trains at sustained speeds exceeding 100 miles per hour, maintain schedules that diesel technology couldn't yet match, and restore public confidence in an industry losing passengers to automobiles and aircraft. More critically, the machine had to prove that steam power still had a future when every industry trend pointed toward obsolescence. Raymond Loewy studied the initial design sketches from his office overlooking Manhattan, where streamlined aesthetics were becoming his signature. As the industrial designer hired to give Pennsylvania Railroad a modern image, he understood this locomotive could define American railroading for decades. But the engineering challenge seemed almost contradictory. The railroad wanted raw power and unprecedented speed, yet demanded a design that wouldn't shake itself apart on curves or terrify passengers with vibration and instability. The solution, emerging from the railroad's Altoona design teams, violated nearly every principle of proven locomotive engineering. While competitors refined existing wheel arrangements and incremental improvements, Pennsylvania Railroad engineers were creating something that had never rolled on American rails. A 6-foot 8-inch driving wheel diameter, a rigid wheelbase stretching over 70 feet, and a streamlined shell that hid engineering decisions most railroads would never dare attempt. The design philosophy behind the S1 began not with the prototype itself, but with a smaller experiment that had railroad officials questioning their own judgment. In 1935, Baldwin Locomotive Works delivered a compact, streamlined locomotive designated K4S number 3847, rebuilt with experimental fairings and tested for high-speed passenger service. The results were encouraging enough to justify a bolder gamble. Chief Mechanical Engineer William F. Kiesel, Jr. reviewed performance data from the modified K4S with the satisfaction of a man whose department was about to receive unprecedented funding. The railroad's board had authorized design work on a prototype that would push steam technology beyond anything attempted in North America. The specification called for a locomotive capable of developing 6,000 horsepower at the drawbar, hauling 1,200 tons at sustained speeds exceeding 90 miles per hour, and doing so with passenger comfort that matched the finest rolling stock in the world. Baldwin Locomotive Works received the contract in 1937 with instructions that revealed how seriously Pennsylvania Railroad was taking this experiment. The wheel arrangement would be 6-4-4-6, a configuration so unusual it required special classification. 2 6-wheel leading trucks would guide the locomotive into curves. 4 massive driving wheels would deliver power to the rails, and another 6-wheel trailing truck would support the firebox and provide additional stability. Nothing like it existed anywhere in the world. The driving wheels themselves represented a calculated gamble on the relationship between wheel diameter and achievable speed. At 84 inches, they were among the largest ever mounted on an American locomotive, chosen specifically to reduce piston speed at high velocities and minimize the reciprocating forces that destroyed conventional high-speed steam engines. The cylinders measured 22 inches in diameter with a 30-inch stroke, dimensions that would generate massive torque while maintaining the smooth power delivery essential for passenger comfort. The boiler design reflected Pennsylvania Railroad's experience with high-capacity steam generation dating back to decades of heavy passenger service. Operating pressure reached 300 pounds per square inch, feeding steam to cylinders through passages designed to minimize pressure drop and maximize thermal efficiency. The firebox consumed coal at rates exceeding 7 tons per hour at full power, requiring a mechanical stoker system that could maintain consistent firing rates regardless of locomotive speed or grade conditions. What distinguished this design from other experimental locomotives was the systematic integration of unproven technologies into a single package. The streamlined casing was not merely aesthetic, but served to direct airflow around the running gear and reduce aerodynamic drag at high speeds. The suspension system incorporated innovations from automotive engineering, using spring combinations that promised to isolate passengers from track irregularities while maintaining the precise wheel contact necessary for safe high-speed operation. By late 1937, as the prototype took shape in Baldwin's Eddystone plant, the wisdom of these radical choices remained entirely theoretical, unproven in service, untested under real operating conditions, and viewed with deep skepticism by engineers whose careers had been built on incremental improvements to established designs. The first technical evaluation of the S1's design arrived at the American Society of Mechanical Engineers with the kind of scathing critique that could end careers. Senior locomotive engineers from competing railroads examined the wheel arrangement, the frame rigidity, and the suspension geometry with growing alarm. Their concerns centered on three fundamental problems that seemed to guarantee catastrophic failure. The 70-foot rigid wheelbase violated every lesson learned from decades of locomotive design. Conventional engineering wisdom held that locomotives needed articulation, or flexible wheelbases, to navigate the curves found on American railroads. The S1's massive frame would theoretically bind on curves, causing wheel flanges to climb the rails and potentially derailing at the exact high speeds the design was meant to achieve. Calculations suggested that curve negotiation would generate lateral forces exceeding the strength of standard rail fastenings. Oscillation dynamics presented an even more terrifying scenario, according to engineers from the New York Central and Santa Fe railroads. At speeds above 80 miles per hour, the reciprocating masses of the valve, gear, and piston assemblies would generate harmonic vibrations that could amplify through the frame structure. The phenomenon known as dynamic augment had destroyed conventional locomotives attempting high-speed runs, causing catastrophic bearing failures and broken frames. The S1's unprecedented size and power meant these forces would reach magnitudes never before encountered in American railroading. The streamlined casing added another layer of concern among maintenance engineers who would be responsible for keeping the locomotive operational. The smooth shell that covered the running gear looked impressive in drawings, but it would prevent visual inspection of critical components during operation. Conventional locomotives allowed engineers and maintenance crews to observe valve gear operation, check for oil leaks, and monitor bearing temperatures while the machine was in service. The S1's shrouding would hide problems until catastrophic failure occurred, potentially at speeds where any mechanical breakdown meant certain derailment. Thermal stress calculations from Baldwin's own engineering department revealed challenges that made even the prototype's designers nervous. The firebox design pushed material limits with temperatures exceeding 2,000 degrees Fahrenheit in areas where conventional locomotives operated several hundred degrees cooler. The combination of high boiler pressure and intense heat created stress patterns in the firebox crown sheets that could lead to explosive failure if water levels dropped even momentarily. Several inspectors noted that existing safety mechanisms might not respond quickly enough to prevent disaster at the firing rates required for sustained high-speed operation. The suspension system drew particular criticism from engineers experienced with high-speed passenger service. The complex spring combinations and load distribution designed to provide smooth riding might work perfectly on test tracks, but would face entirely different forces on real railroad main lines, with imperfect track geometry and varying rail conditions. Critics pointed to the physics of unsprung mass and predicted that the driving wheels would lose contact with the rails at high speeds, creating conditions where the locomotive would effectively become airborne for fractions of a second before slamming back down with destructive force. Financial analysts added their own damning assessments to the technical criticisms. The S1 would cost approximately $600,000 to build, equivalent to 3 conventional passenger locomotives of proven design. If the prototype failed during testing or proved unsuitable for regular service, Pennsylvania Railroad would absorb a loss that shareholders were unlikely to forgive during an era when railroads were already struggling against automobile and aircraft competition. The mechanical department's reputation and future funding depended on success, making the prototype's rollout one of the highest-stakes gambles in American railroad history. The S1 emerged from Baldwin's Eddystone Works on January 26, 1939, riding on specially reinforced railcars for the journey to Altoona. The locomotive's dimensions required careful route planning, as standard clearances barely accommodated the streamlined casing that stretched over 140 feet from coupler to coupler. Crowds gathered at crossings to witness the gleaming maroon and gold machine that represented either the future of American railroading or an expensive mistake about to be exposed. Lead test engineer Marcus Thompson watched the S1 roll onto the Altoona dynamometer track with the methodical attention of a man whose career would be defined by the next 6 months. The testing protocol called for gradually increasing speed and power measurements while monitoring every bearing temperature, frame stress point, and vibration frequency. The first runs would barely exceed 30 miles per hour, building confidence in the basic mechanical systems before attempting the high-speed performance the design promised. The initial low-speed tests revealed characteristics that surprised Thompson's team in ways the critics had never predicted. The massive locomotive started its 1,000-ton test load with such smooth authority that dynamometer needles barely flickered during acceleration. The 6-4-4-6 wheel arrangement distributed weight so effectively that rail stress measurements came in well below theoretical maximums. Most surprisingly, the rigid wheelbase that was supposed to bind on curves negotiated the test track's tightest radius with flange contact pressures no higher than conventional articulated designs. Speed runs began in March of 1939, incrementally pushing the S1 toward the performance envelope its designers had promised. At 60 miles per hour, the locomotive developed drawbar horsepower exceeding 4,000 with coal consumption rates that were actually lower than predicted. The streamlined casing was proving its worth by reducing aerodynamic drag, allowing the S1 to maintain higher speeds with less steam flow than conventional exposed running gear designs required. The vibration characteristics that had terrified consulting engineers simply failed to materialize in the ranges predicted by their calculations. At 70 miles per hour, accelerometers mounted throughout the frame recorded oscillation amplitudes well within acceptable limits. The suspension system was performing exactly as Pennsylvania Railroad's designers had intended, isolating the locomotive from track irregularities while maintaining constant wheel contact. Thompson's reports back to the mechanical department noted that passengers in a test coach coupled behind the S1 experienced smoother riding than in trains hauled by conventional K4S locomotives on the same track sections. By May, the testing protocol had advanced to sustained high-speed runs that would either validate the design or confirm the critics' worst predictions. Thompson authorized a test sequence calling for 90 minutes of continuous operation at 90 miles per hour, conditions that would generate the thermal stresses and dynamic forces that supposedly guaranteed failure. The S1's crew fired the locomotive to maximum boiler pressure, opened the throttle to positions that would have destroyed lesser machines, and settled into a rhythm that consumed coal at rates exceeding 6 tons per hour. The dynamometer trace from that test run would become one of the most studied documents in American locomotive history. For 93 consecutive minutes, the S1 maintained speeds between 88 and 92 miles per hour while developing drawbar horsepower that peaked at 5,800. Bearing temperatures remained stable throughout, frame stress gauges showed no unusual patterns, and the reciprocating components that were supposed to shake the locomotive apart continued operating with mechanical precision that validated every radical choice Pennsylvania Railroad's designers had made. The prototype that engineers had called dangerous was proving to be the most stable, high-speed steam locomotive ever tested in North America. The S1 entered revenue service on the Broadway Limited in April 1940, assigned to the demanding Chicago to Crestline segment where sustained high-speed running could demonstrate whether testing success would translate to operational reality. Veteran engineer Bill Deckert received the assignment with mixed emotions, having spent 20 years operating conventional locomotives that obeyed predictable mechanical laws and never surprised their crews with unexpected behavior. The first revenue run shattered every assumption Deckert had formed during his orientation sessions. Departing Englewood Station with 18 cars trailing behind totaling 1,200 tons, the S1 accelerated with such authority that Deckert found himself throttling back to avoid exceeding track speed limits before the train had fully cleared Chicago's industrial districts. The locomotive responded to throttle inputs with the immediate precision of a machine half its size, building speed smoothly through ranges where conventional locomotives would have been laboring with maximum steam flow. Open country running between Fort Wayne and Crestline provided the S1 its first opportunity to demonstrate the performance that justified its radical design. With clear signals and straight track ahead, Deckard advanced the throttle to positions he had never used on conventional locomotives and watched the speedometer climb past 80, then 90, then touch 97 miles per hour with steam pressure remaining solid and no indication of mechanical distress. The vibration that critics had predicted would shake the train apart was barely perceptible in the cab, less than Deckard experienced regularly with standard K4S locomotives at 20 miles per hour slower. Passenger feedback collected by Pennsylvania Railroad's customer service department revealed the S1's impact on public perception of train travel. Business travelers who had increasingly chosen aircraft for Chicago-New York trips began requesting Broadway limited schedules specifically to experience the streamlined locomotive's performance. Complaints about rough riding and vibration, common with conventional steam power, virtually disappeared on S1 hauled trains. The smooth acceleration and sustained high speeds created a travel experience that matched the railroad's advertising promises about modern luxury service. The mechanical performance proved equally impressive in ways that silenced critics who had predicted maintenance nightmares. After the first month of service, totaling 4,200 miles, inspection revealed bearing wear patterns well within acceptable limits and no signs of frame stress or suspension problems. The streamlined casing that was supposed to hide developing problems actually protected running gear from weather and trackside debris, reducing maintenance requirements compared to exposed conventional designs. Boiler performance remained consistent with no evidence of the thermal stress failures that engineering calculations had suggested were inevitable. Coal consumption data provided economic validation for the prototype's continued operation. The S1 averaged 2.4 pounds of coal per drawbar horsepower hour, significantly better than the 3.1 pounds typical of conventional K4S locomotives hauling similar trains. The improved efficiency resulted partly from reduced aerodynamic drag, but primarily from the sophisticated steam distribution system that minimized throttling losses and maintained cylinder efficiency across the locomotive's entire operating range. Operating cost per mile came in 17% below conventional power despite the S1's larger size and higher initial cost. By summer 1940, the S1 had logged over 30,000 miles in revenue service with availability rates exceeding 92%, better than the fleet average for conventional passenger locomotives. The machine that engineers had labeled too dangerous for regular service was outperforming proven designs while requiring less maintenance and delivering passenger satisfaction that translated directly into increased ticket sales. Pennsylvania Railroad's gamble was paying dividends in ways that extended far beyond mere technical validation. The performance data that accumulated through 1941 forced a direct comparison that Pennsylvania Railroad's conservative engineering faction had hoped to avoid. Standard K4S locomotives, the proven workhorses that had hauled the railroad's premier passenger trains for 2 decades, were being systematically outperformed by the experimental design they had opposed. The numbers told a story that undermined every argument against radical innovation. A K4S Pacific hauling the same 18-car Broadway Limited consist required an average of 4 hours and 43 minutes for the Fort Wayne to Crestline segment, operating within speed limits that reflected the locomotive's mechanical capabilities and track authority restrictions. The S1 covered identical trackage in 3 hours and 58 minutes. Maintaining schedules that allowed Pennsylvania Railroad to advertise competitive journey times against aircraft while providing superior passenger comfort. The 45-minute difference represented not merely faster running but the ability to absorb delays and still maintain published arrival times. Fuel efficiency comparisons revealed advantages that translated directly to operating economics. The K4S consumed an average of 12 tons of coal for the Crestline run, while the S1 required 14 tons, seemingly worse until engineers factored in the work performed. The S1's higher average speed meant it was moving the same tonnage through significantly more distance in less time, resulting in lower fuel cost per passenger mile and better equipment utilization. The railroad could operate fewer trains to carry the same passenger volume, reducing crew costs and track maintenance expenses. Maintenance intervals told an even more surprising story that contradicted predictions about the S1's operational complexity. K4S locomotives typically required running gear inspection every 3,000 miles, with bearing servicing at 6,000-mile intervals. The S1's protected running gear and improved lubrication systems extended inspection intervals to 5,000 miles, with bearing work postponed until 10,000 miles of operation. The streamlined casing that critics claimed would hide problems was actually reducing contamination and wear, resulting in longer component life despite higher operating speeds and greater power output. The most dramatic difference emerged in passenger experience measurements that Pennsylvania Railroad began collecting through systematic surveys. Passengers who had ridden both K4 S-hauled and S1 hauled consistently rated the experimental locomotive consistently higher for smoothness, with 68% describing the S1 experience as superior to conventional trains. Comments specifically mentioned reduced vibration during acceleration, quieter operation at cruising speeds, and the ability to walk through cars and conduct normal activities without the swaying and jolting typical of traditional steam power. Track maintenance records provided unexpected validation of the S1's superior engineering. Despite operating at higher speeds and developing greater power, the experimental locomotive caused less rail wear and fewer alignment problems than conventional designs. The weight distribution across the 6-4-4-6 wheel arrangement spread dynamic loads more evenly, reducing peak stresses that caused rail fatigue and joint failures. Track engineers reported that mainline sections regularly used by the S1 actually required less maintenance than comparable routes served exclusively by K4S power. The comparison extended to crew preferences, where conventional wisdom suggested engineers would prefer familiar proven designs. Surveys of qualified engineers who had operated both types revealed 73% preferred the S1 for long-distance passenger assignments. The reasons cited included easier throttle control, better visibility from the cab, reduced fatigue from smoother operation, and confidence in the locomotive's ability to maintain schedule regardless of operating conditions. The machine that was supposed to terrify crews was becoming the preferred assignment for the railroad's most experienced engineers. The strategic impact of the S1 extended far beyond its technical achievements or operational statistics. By 1942, as wartime traffic pushed American railroads to capacity limits, Pennsylvania Railroad's willingness to gamble on radical innovation had created competitive advantages that translated directly to financial performance and public confidence in steam technology's continued relevance. The S1's success influenced immediate design decisions across the railroad's motive power program. Baldwin Locomotive Works received orders for additional streamlined locomotives incorporating lessons learned from the prototype, including improved versions designated T1 class that would eventually number 52 units. The validation of high-speed steam technology gave Pennsylvania Railroad credibility in debates about post-war equipment modernization, allowing the mechanical department to argue successfully for continued steam development rather than immediate conversion to diesel-electric power. Passenger revenue data revealed the prototype's impact on public perception and travel choices. Ridership on S1 hauled Broadway Limited increased 23% compared to identical trains powered by conventional locomotives, with customer surveys indicating that the streamlined locomotive's presence influenced booking decisions. Business travelers who might have chosen competing airlines specifically requested trains scheduled for S1 operation, creating marketing value that exceeded the locomotive's direct operational contributions. The engineering community's reassessment of the design they had initially condemned came through technical papers and industry presentations that acknowledged how thoroughly the prototype had invalidated conventional assumptions. The American Society of Mechanical Engineers published detailed analyses of the S1's suspension geometry, thermal efficiency, and high-speed stability characteristics, providing data that influenced locomotive design across multiple railroads. The 6-4-4-6 wheel arrangement that had seemed dangerously experimental became the basis for serious engineering studies by competing roads seeking similar performance advantages. Wartime service demonstrated the S1's strategic value under conditions its designers never anticipated. With passenger traffic tripling and equipment shortages forcing railroads to maximize utilization of every available locomotive, the S1's superior efficiency and reliability became critical assets. The railroad operated the prototype on schedules that would have required 2 conventional locomotives to maintain, effectively doubling motive power capacity through superior engineering rather than additional equipment purchases. Maintenance crews kept the S1 in service 94% of available hours during 1943, availability rates that proved the design's fundamental soundness under the most demanding conditions. The prototype's influence extended into the post-war era, when Pennsylvania Railroad faced decisions about equipment modernization that would define the company's future. The S1's demonstrated performance provided justification for ordering the T1 class production locomotives rather than committing entirely to diesel power, buying time for steam technology to prove its economic viability against emerging competition. While dieselization eventually proved inevitable across American railroading, the S1's success delayed that transition long enough for Pennsylvania Railroad to maintain service quality and competitive position during a critical period. The ultimate measure of the S1's success came not from performance statistics or maintenance records, but from its demonstration that engineering courage and willingness to challenge conventional wisdom could produce results that exceeded every expectation. The locomotive that engineers had called dangerous, that critics had predicted would fail catastrophically, that conservative railroaders had opposed as reckless experimentation, became the machine that proved exactly what American railroading needed. Innovation over caution, performance over convention, results over reputation. 80 years later, the S1 stands as proof that the most dangerous engineering decision is often refusing to attempt what seems impossible. The S1's legacy resonates through every high-speed rail system operating today, though few engineers recognize the debt modern transportation owes to a 1939 prototype that dared to ignore accepted limits. When Japanese engineers designed the Shinkansen bullet train in the 1960s, they studied Pennsylvania Railroad's documentation of high-speed stability and aerodynamic efficiency. When French railway developers created the TGV, they referenced American research into sustained triple-digit speeds that began with the S1's testing program. The prototype itself was scrapped in 1949, its massive frame cut apart for wartime steel recovery, but the engineering principles it validated survived in every locomotive design that followed. The willingness to challenge conventional wisdom, to build what critics called impossible, to trust calculations over conservative tradition, these became the foundation of modern rail engineering. Today, streamlined trains routinely exceed speeds the S1's designers could barely imagine, operating with safety records and efficiency levels that validate every radical choice made in 1937. The dangerous prototype that engineers feared became the catalyst that proved steam technology's final evolution and demonstrated that the greatest risk in engineering is not bold innovation, but timid acceptance of limitations that exist only in collective imagination. The railroad it saved was not just the Pennsylvania Railroad, but the entire concept that ground transportation could compete with the emerging age of aviation.